Okay, so we're going to move on to continuity. If I go too quickly, you can just hit pause, obviously. But this should be, most of these ideas you should be familiar with already. So, we say that a function is continuous if it's continuous at each point of its domain. A function's continuous at an interior point, we'll call it point C, of its domain, if the limit as x approaches c of f of x equals f of c. So now remember, we're talking about whether a function is continuous or not, and then the other idea is talking about if it's continuous at a particular point. So those are two distinct ideas. So let's look at an example. I have this well-drawn sketch of a function, passes the vertical line test. So let's look at a few of these. What's the limit as x approaches 1 from the left? Maybe I need to create a dot. There we go. So if we're traveling along this curve as we approach 1 from the left, obviously we are approaching 0. Okay, what's the limit as x approaches 1 from the right of this function? So now, we're moving along this way, approaching 1 from the right. And what would that limit be? Well, that's constant, so that limit is just 1. Alright, let's scroll a little. Squeeze that in there. So what's the limit as x approaches 1? Well, in order for that limit to exist, we need the left-hand and the right-hand limit to be approaching the same value. And in this case, they're not approaching the same value. One is approaching 0, the other is approaching 1. So we say that the overall limit does not exist. So in order for a limit to exist, we have to check both the right and left side, unless, of course, it's an endpoint, and then we just have to check from one side. Two other questions. What's the limit as x approaches 2 for this function? So, once again, if we approach 2 from the left, that would be this way. What are we approaching? We're approaching the value of 1. And as x approaches 2 from the right, traveling along this function, we're also approaching the value 1. So in both cases, our left and right-hand limits are the same. So the limit as x approaches 2 is equal to 1. What is f of 2 though? Well, our function value at x equal 2 is 2. It jumps up. And so this is another case where our function is not continuous. So it's not continuous at x equals 1, and it's also not continuous at x equals 2. And as I've mentioned, a function is continuous at an endpoint if the one-sided limit exists, and the limit has to equal the value of the function at that endpoint. So looking back again at this, where's my graph? Up here. If we say what's the limit as x approaches 4, then we can only consider the left-hand limit, and that limit is 1, and f of 4 equals 1, so it's continuous at 4. It would also be continuous at 0 because the one-sided limit and the function have the same value. Okay, so we have a continuity test. And now you have to be careful. Here we're talking about a function being continuous at a point. So a function is continuous at a point C if and only if all three of the following have to be true. So I'll show a counterexample for each one as we go through it. So first, f of c has to exist. So let me give you an example where that would not work. So let's say we have our function here. Here's x equals c. And let's say our function f looks something like that. Okay, obviously this function is not continuous at c because f of c does not exist. The second part that has to be true, the limit as x approaches c has to exist. So if you notice in that first picture, the limit does exist, but f of c does not exist. So let me show you a case where f of c exists, but the limit does not exist as x approaches c. So we could have something, let's say, like that. So here, oops, I didn't label this as c. There we go. So here, f of c does exist, so the first test passes, but it doesn't pass the second test. The limit does not exist because the right and left hand limits are different. Okay, and the third and final test is that the limit as x approaches c of f of x has to equal f of c. So let me draw a case where it passes the first two tests but doesn't pass the third test. So here's c. So we could have something like that. So the first f of c exists, check. Does the limit as x approaches c exist? Check. But the limit does not equal the value of the function. So all three of those, that's your three-part test for continuity at a single point. All right, let's look at some examples. Is y equal 1 over x continuous? This is one that always throws students. Usually I get quite a few that say, no, it is not, because it's not continuous at 0. But if you go back to the first definition I gave you, if a function is continuous, it has to be continuous at every point in its domain. And x equals 0 is not in the domain of this function. So at every point in the domain, this function is continuous. It passes the continuity test. So we would say that y equal 1 over x is continuous. Now, if I asked you, is y equal 1 over x continuous at 0, then the answer to that would be no. All right, how about this example? Let's look at this rational function. F of x is equal to x squared minus 3x all over x minus 3. Is that continuous at 3? So now first of all, you recognize that 3 is not in the domain of this function. So we know there's a problem. But could we fix this function so that it would be continuous at 3? And so here we have to investigate a little further. What's going on at x equals 3 or around x equals 3 for this function? Well, if you notice, for this function, I could factor an x out of the top. And as we've learned before, in this case, where you have factors and one of the factors in your denominator cancels with a factor in the numerator, then that means that we have a hole in the graph at the value that would make that 0. So at x equals 3, we have a hole in the graph, and that we can fix. On the other hand, if we weren't able to cancel the x minus 3 factor, then it would be an asymptote, and we can't fix that. That's too big a problem. But with a hole, all we need to do is plug in the hole. So the function f of x equals x, after we simplified this, actually I shouldn't even write f of x. Let's call that g of x equals x. G of x is exactly the same function as f of x, except at one single point, at the value x equals 3. So f of x has a hole. It's actually the line y equals x with a hole at x equals 3, and g of x doesn't have the hole there. So all we want to do is figure out what's the y value where that hole is, and we can figure that out by evaluating g after we had canceled the factors, and that'll be 3. So in this piecewise function, we've got f of x for all the values in its domain, and then we're going to add this one, and that's basically just filling in the hole. So we call that a removable discontinuity. We're able to fix that problem. All right, so for what values of this function or for what values of x is this function not continuous? So what's the first thing we need to do? Well, we should figure out what's the domain of this function. And anything that would make the denominator 0 is a problem, so that would be x equals plus or minus 2. So it's not continuous at 2 or negative 2. Are either of these removable discontinuities? Well, once again, let's try and factor and see if anything cancels. If a factor in the denominator cancels, then it's just a hole in the graph and we can fix that. So when you factor this, the x minus 2 cancels, which means at x equal 2, there's a hole in the graph, so that's the one we can fix. So we can rewrite this function and call it x squared plus x minus 6 over x squared minus 4 for all values except for x equal 2. And then at x equal 2, we're going to plug in the hole. And once again, how did we figure out what that is? We'll go up here, and after we canceled the x minus 2's, now if I plug 2 into there, I get 5 over 4. So that's how you figure out what value should go in where the hole is at. Alright, we have some properties of continuous functions. And since they're tied to limits, this always goes back to some of our properties for limits. If f and g are continuous at a point x equals c, then each of the following are also going to be continuous at x equals c. So the sum of the two functions, f plus g, that'll be continuous at c. The difference of the two functions will be continuous at c. The product, a constant times one of the functions, and the quotient as long as we don't get a divide by 0. And then the one that's not quite as obvious is composition. So f of g of c, or g of f of c, will also be continuous. So that's it.